Hi everyone, and thanks for voting for this talk. Thanks again for putting in the last slot of the day. Okay, that is just a joke. About me, I work for ThoughtWorks. We've been in Singapore for almost close to a year now. Our office is actually just across the road at Cecil Street. That's a geek Martin Fowler in one of his laid back moves. I've been a contributor to this library called Neo4j.rb, which are the Ruby bindings for Neo4j. So that's where my interest in graph databases and how all of this stuff works really came about. My main contributions have been to these three areas: multitenancy, versioning, and performance. I'll be talking about the first two a little bit. I'm also the author of Frankenstein, which is a functional testing tool for Swing applications. Nobody does Swing anymore, so that's that. Okay. Here's what we have for today's talk. It's essentially divided into 3 bits. We'll start off with a graph primer. We'll go over some graph theory and basically what it takes to put graphs together. We'll talk a little bit about what you can use graphs for. And finally, we'll take a look at a few examples. The examples are going to use Neo4j.rb, but in a lot of senses, they're portable and can be used with any language that you like. Okay? So let's start off with a primer then. What's a graph? Anybody in the audience? No.
A series of nodes and edges.
Okay. So this is the Wikipedia definition, which is a bit abstract of course. It says a graph is an abstract representation of a set of objects where some pairs of objects are connected by links. Right? Graphs are actually all around us. If any of us are software developers, we talk about object graphs. So we talk about a customer choosing end products, placing an order for end products, and then maybe getting that order fulfilled. The object graph, of course, this is how we'll typically model, say, an order process, but this fits in within a much larger context. That may be what your runtime environment looks like, for instance. If you're Indian, you will see graphs of another sort. So that's his grandpa, that's what Tata means. So his question is, who is Chachu Chitti? Right? Okay, this is one of those rare situations where you ask a question and you get back a graph. Right? That's usually rare, as you will see. Okay? Oops. Okay. Does anyone know what this is? This is the best image I could find of this particular city.
Königsberg
Yeah,
Bridge.
exactly. So this is, the city is Königsberg, and the name of the river is called Fregel, which is also the name of a tool that Google recently came out with. They wrote a paper about it. But essentially, what this is about is those green things that you see there are bridges, and the blue that you see there is the river. The problem is basically, how can you go across each of those landmasses by crossing each one of those bridges just once? So this particular problem or riddle, whatever you want to call it, is the origin of graphs and graphs theory. Right? So the person who first took a crack at solving it is Euler, the great Swiss mathematician. In case you didn't know, Euler is the guy who actually popularized the use of pi, the sigma notation, the f of x kind of notation that you use in mathematics all over the place. Now this next one has nothing to do with graphs, but I thought I must put it in. Richard Feynman called this the most remarkable formula in mathematics. There's actually a magazine of mathematics, it seems, and the readers of this thing apparently voted this the most beautiful mathematical formula of all time. It's quite beautiful and crazy at the same time because it puts together two transcendental numbers, e and pi, and has something to do with imaginary numbers as well. So coming back to the original bridges of Königsberg problem, Euler actually solved this particular problem using logic. I won't really get into the details of the solution, but the logic that he put together really forms the origins of what we know as graph theory. Right? So you can have many, many different kinds of graphs. This is an example of something that's called an undirected graph. So essentially you have 3 nodes and they're connected by edges, but there's no direction to those relationships at all. You can also have something called a directed graph, where you have nodes and you have relationships between those nodes, but the direction of those nodes is important. So now to give you a better example, you could say that that's me in the corner, and that's Andy sitting in the audience. So Andy knows me, and I know Paul. Paul is not present in this particular talk right now, of course. But I can start adding a little bit more information about this. Since when does Andy know me? He knows me since April, right? But I know Paul for quite a bit longer than that. He was on my first project at ThoughtWorks, and I know him since September. So you see what's happening here? As we are adding more and more information to the graph, it starts getting richer and richer. And you can actually figure out things like since when, or if we added some more information like what are the projects that we worked on, you could possibly figure out things like did Andy and me work on the same project together? What are the projects that Paul worked on after he first worked with me? What are the projects Andy worked on? And so on and so forth. Yep. So here's another example. Let's say that you had Hercules, and Jupiter was his dad. Alcmene is his mother, right? And let's say that you wanted to ask the question, is Hercules a demigod? Right? So very, very simple graph, just 3 nodes and 2 relationships. So how do you actually answer the question? So you'd say something like this. You'll try and figure out whether, so what's the definition of a demigod? A demigod is somebody who has one parent who's a god and another parent who's a human. So let's try and answer that question from this little graph that we have right here. So the language that you see down there is something called Gremlin, which is kind of an open standard as far as graph traversal is concerned. It's one of the many ways in which you could solve this problem, but we essentially start by asking this question. From Hercules, let's find out his parents, that's what the mother and father is for, and then let's try and find out who they are, or what type of people were they. And for this particular graph, if we ask the question, the answer that we get back is, of course, that Hercules had one human parent and one parent who was a god. Now that we know this, we can actually add to the graph. And we can actually say that Hercules is not just Hercules, he's also a demigod. So again, similar to that first little example that we saw, in which we talked about people knowing each other and so on, as we infer or learn more about what information is out there, we can actually start adding and building to the graph itself. And this is again a pretty common characteristic of graph databases. So in other words, as we learn something new about the data that we have based on the result of a query, we can actually add that information back into the graph. Right? So what is a graph database? So essentially, it's a database in which the graph structure is explicit. So yes, you can use other technologies like relational databases and maybe even document databases to model graphs, but there you need to figure out a structure and a scheme to actually model it. So what I mean by that is that yes, you can represent a graph in many other database types, but the thing that you're dealing with are things like tables, rows, foreign key constraints, and so on and so forth. You're not really dealing with nodes and relationships explicitly at all. And that's really what graph databases try to do. So in a graph database, each node knows its neighbors, and typically the kind of graphs that you tend to have are directed graphs. So you'd have something like this, where you have a node that's connected to other nodes, and the direction of the relationships matters, and you try to figure out what else you're connected to. So this is also a good way to model or think about how to put together graphs. So just like when you are dealing with a code base, you're not going to keep every single class or every single object in your mind all the time when thinking about it. You probably do something like think about one class, think about the other classes that it collaborates with, right? And then move on to the next thing that you're trying to model. So rather than looking at the entire object model in its entirety, you probably go step by step, bit by bit. And that's probably a good way to look at modeling graphs as well. So a good way to think about it is to start at a particular place in the graph, and then to look at who your neighbors are and how you're related to them. Okay. So there are 2 main operations that you can do if you are trying to query graphs. You can find nodes. Yep. And you can do this either explicitly, which is by specifying the identifier of the node. This is similar to what you do with something like MongoDB, where you refer to a document by its ID. You could also use an index. Most graph databases have some sort of integration with search technologies. So, for instance, with Neo4j, you can do something like this. So you can say that if I have many cars in my graph database, I can find all cars that start with the name APRR. Okay? So you probably just get back one answer, but it allows you to do these kind of fuzzy queries quite easily. The other thing that you can do is that you can traverse a graph given an origin. Okay? Now we're going to go a little meta. So this is a graph that represents how you put together a graph database. So it's a graph about a graph. Okay? So I'm going to spend a little bit of time on this one. Do you want me to ask you any questions about it? Probably not at this time. So I'll try and explain some of the things that we have here. So we're saying that a graph database manages two things, indices and graphs. Now you can index a relationship or you can index a node. The graph consists of two things, relationships and nodes. Both relationships and nodes can have properties. Now let's ask a few questions. So what are the things in a graph database that have properties? As you can see, if we answer that question, we have two things. We have relationships and we have nodes. How does a graph database record its information? Again, by looking at this, we can say that we record our data in relationships, and then we record our data in nodes. Yep. So how did we answer those questions? You could say that we did it a little bit with intuition, but you're starting to get a feel for what a graph database or graph data and what kind of queries that you could run against that data could look like. So they're slightly different from what you may be normally used to, but they actually enable you to answer some pretty interesting questions. Yep. Okay. So moving on, there's a whole family of graph algorithms, which I'm sure a lot of you would be familiar with. The most common one, of course, is shortest path. So given these 5 nodes, which are all related to each other, some of them directly, others indirectly. Let's say that I wanted to find out what's the shortest path from the red node on the left to the red node right on top. Right? How do we actually get there? So the places where this kind of thing is applicable is if you use a website like GoThere.sg, where you're trying to find out how do I get from here to Changi Airport, and you're trying to find out things like which is the best way or the quickest way to get there. You could say I'm interested in optimizing time, which means I want to get there as fast as possible, and then it's probably going to tell you things like maybe the MRT is still faster than a taxi, right? Now, if you want to optimize on cost and you'd like to figure out things like what's the cheapest way to get from here to Changi, you could get another answer altogether, right? So the main thing is that what we're trying to do is represent the cost of what it takes to get from node A to node B, and answering the question of finding out the shortest path will tell us the optimal way to get there. So the interesting thing is most graph databases have these algorithms built in. So you can actually go to a graph. So I'm not sure if that's 100% visible at the back, but essentially what we're saying is starting at node 1 and maybe at node 6, which represents those two red things that you saw there. Let me find out what are all the shortest paths from these two things. and what is the cheapest way to get there. Yeah, I'll show you a better example on the presentation. Okay, so moving on, what are the options that you have in case you're thinking about using a graph database? So at this point, there's several of them. Right? Neo4j is probably the most well-known of them. It's been around for close to a decade now. Other ones are OrientDB, Titan, which is actually a pretty recent graph database. The thing that's interesting about Titan is that the backend data storage is pluggable. So you can think about using it with databases like HBase and Cassandra, and you can actually distribute your graph, which actually is one of the hardest things to do as far as graph databases are concerned. So I was thinking about where the name came from. Maybe it's from the sequel to the Titans movie. So maybe that's the next in the series. Okay. So the examples that we're going to take a look at will use Neo4j. Yeah. So what is Neo4j? Essentially, it's an ACID-compliant graph database. This is a characteristic that is quite different from most of the other NoSQL stores. So, for instance, you can't really do transactions in something like MongoDB. You can mimic them, but you can't really do them. And in fact, if you look at the documentation, you'll see that it's not usually recommended to build things like financial systems in some of the document-oriented databases because they don't really have transactions. You have to mimic them or simulate them by whatever mechanism. With Neo4j, though, you have an ACID-compliant database, which means that you can basically modify a graph in a concurrent environment and make sure that the data is updated correctly. So this is something that this is a blurb that the Neo4j guys usually use in their presentations. I just wanted to point it out. There's something quite funny about it. It says, graph databases like Neo4j are an esoteric but powerful member of the NoSQL family. It's almost as if the database is radioactive and we should not use it because it might blow up or something like that. I find it quite interesting because in my experience at least, it's not been esoteric at all. So when you look at the graph data and how it's interconnected, yes, it can probably freak you out in terms of how interconnected and crazy it looks. But in terms of how you use it as an end user, it's usually fairly straightforward. Yep. Okay. So what kind of capacity are we talking about? So with Neo4j, you can do something like 32 billion nodes, 32 billion relationships, and around 64 billion properties. That's a lot more than what you usually need to use in most scenarios. So this is how much one database instance can handle. And if you have data that's even more than that, then you can think about partitioning it across multiple database instances. So the database is thread safe. It allows you to do single depth transactions. What I mean by that is that when you open a transaction to make a change to the database, you can't open another transaction within it and then have it behave the right way. So if you do nested transactions, a nested transaction is something that's called a placebo transaction, which means that ultimately, when you open a transaction, you can have a maximum of one thing that's open at the same time. If you open a nested transaction, it basically does nothing. So that's why it's called a placebo transaction. The interesting thing is that it has Lucene integration as well, and the Lucene index gets updated as part of the transaction. This is actually a pretty big deal. I heard somebody asking a question about Mongo and full text search and what tools to use and all of that from the previous talk. This is something that Neo4j is actually pretty good at. Just give me a second. Let's look at some examples. Okay. So let me just do it from scratch. It's going to be a bit hard to. Can I have a volunteer, please? Just hold the mic. Thanks. Thanks a lot. Okay, so what we're going to do is, I already have. Come a bit closer. Down a little. Thanks. Okay, this is going to be really hard. Sorry about that. Okay, we'll figure out a way. But essentially, what we have is a location class. It extends from Neo4j Rails model. You can't see that. So it has a single property called name. It has a full text index as well, right there. So that's basically how you define an entity or a node if you're using Neo4j from the Rails side. So quite simple. You define the name of your model. It extends from one class, and then you have to explicitly define the properties that you have. Now, you need to do this only if you want to index these properties. Now, indexing in the graph world means something slightly differently from what you do in the database world. When we talk about indexing, we are talking about improving query performance. When we say index here, we are really talking about making it available for a Lucene search. So it's a search kind of indexing that we're talking about in this particular case. Yep. So let's give that a shot. Now that we've seen the definition. I'm just going to switch this off. So let's create a new location. We're going to give it a name. Let's call it GeekCamp. I know that's not a location, but that's it. Okay. So we get back an object. Right? We haven't saved it to the database yet. This is still an in-memory representation. So the next thing that we're going to do is save it. Now that it's saved, let's try and retrieve it back from the database again. So as you can see, the location object that I just created can now be found via Lucene, via that simple API that you see there. So the thing that you see in a string which says name geek star is actually a Lucene query. This is what I meant when I said that the Lucene index is actually updated when you actually save things to the database. So you don't need to run a MapReduce job or a background process or anything else to actually keep your index up to date. The database does that for you automatically. And that makes it really useful because then as your system generates data and as you create relationships and nodes and link everything together, you can actually pretty much start querying the data immediately. So we call this near real-time search. Right? And it's something that Lucene actually makes possible. But the nice thing is that it's when you integrate Lucene with the database, it actually gives you something that's really powerful. Okay? So
the indexes, the Lucene indexes, those are created on like key properties itself, or like on the entire object?
Okay. So his question was, are the indices created on key properties? Yes, the properties, the indices are created on properties, but they also put under the main object that you're working with. So when the indices are organized on disk, you'll usually find something like location / the name of the property that we just indexed, which was name. Right? The type of index is something that you can control. So you can actually say whether you want an exact index or a full text index. So if you want to do a fuzzy kind of search, similar to the one that we just did, then you'd say full text. But if you wanted an exact match kind of search where you have to say exactly what you're looking for, then you just have to specify that index as exact. Yeah. Okay. So here's the other interesting thing. Now, let's say that you wanted to find out all the locations that we have available. So you'll notice that what you get back is not a list. It's actually something called a traverser. It's like an iterator. It allows you to go through all the entries that you have. So essentially, if you look at what this looks like now, even though we're dealing with a graph, when you model it, it's very similar to what you do if you're working with objects. So we talk in terms of locations. Locations could be linked to other locations, and so on. So if you remember that order and product example that we talked about earlier, you could say that you have an order, it extends from Rails model as usual. You could say that it has n products. This is how we specify relationships between nodes and other nodes, right? So if you want to see what the product looks like, there's pretty much nothing in there. It just extends from Rails model, and that's about it. So I'm aware that some of you may not be familiar with the Ruby in the audience, but the main thing, like I said earlier, is that some of these things that we're covering are not language or framework specific. These are concepts that are applicable across languages. So the main thing that to take away here is that we can model nodes in using pretty much any language that you like, and we have facilities to basically define relationships between nodes and other things in the system. Yep. Does that make sense? Moving on. Yep. I'll cover that in a short way. Yep. So his question was, how do you handle migrations? So we'll cover that in a short way. Okay, just give me a second. Okay, for some reason, try to print my presentation. Okay, so that's how the Lucene integration works. As you saw, it happens within the transaction. It actually uses two query languages, which you actually saw in the early stages as well. So one of them is called Cypher, which is more of a declarative kind of query language. So where you say, find me the shortest path between these two nodes, look for a maximum of 15 hops between these two nodes, right? Or you could say, find me the total cost of getting from here to Changi, assuming a maximum of 3 hops. Or have Andy and me worked on the same project before in 2003. The other one is called Gremlin. Gremlin is more of an imperative kind of query language. So we saw that in the Hercules example. So there you have to say exactly how you'd like to get from point A to point B. So with Gremlin, you have to specify the order or the way in which you're going to traverse through the graph yourself. Okay? That's useful if you'd like to do something sophisticated, or if you'd like to control the way that you traverse the graph on your own. So with Neo4j, there are advanced and enterprise editions that are available for doing things like monitoring, replication, and backup. Word of caution, those two editions are really, really expensive. We're talking about $2,000 a month or something like that. Okay. Apparently, if your application is open source, it's free. So that's up to you. Okay. So what can you use graph databases for? So the typical application that you will find, so if you have a fairly complicated set of security rules, for instance, where you'd like to model a system where you have very fine-grained permissions to various parts of your system, that's one place where representing that in a graph may make sense. So for instance, if we have specific permissions for a specific part of the system for specific users, it's possible to model that fairly easily in a graph. If you're doing this with a regular database, it may be a lot more work. Another similar kind of situation where you have access to parts of the system for generic groups of users, but you'd like to have specific permissions for individuals who may or may not belong to those groups. Another really common example of what graph databases can be used for is recommendation systems. So on Facebook, if whenever Facebook tells you you may want to be friends with this person, it's because they've traversed the object graph or the relationship graph between you and your friends, and they've tried to figure out things like like other people who are friends with the same friends that you have, for instance, right? So, for instance, Amazon does this quite a bit too. So, for instance, if the dinosaur-like thing on top watches the same movie as the thing with the mushroom, then maybe that's a recommendation for the guy in the suit. I have no idea what's here. Okay. You can also use graph databases for fraud detection. Basically, when we try and detect fraud in financial systems, it comes down to what we call as tracking the money trail, right? And you can do that fairly easily with a graph. So in other words, you'd like to figure out where money is going, who's transferring money to whom, to what shady account in some weird part of the world has somebody transferred money to, and who took money out of there back to some other part of the system. So if you have the information about what transactions were done and who transferred what amount of money to what location, it's possible for us to trace it all the way back and detect things like money laundering and so on, which is actually a fairly interesting kind of application. You can also use it for geospatial analysis. So one of the things that graphs are really useful for is partitioning spatial information into a way in which it can be traversed. So for instance, does anyone know what this is? Yes, I know it's a rabbit. But what's the thing that's around it?
Was this used for CFD?
I have no idea what that is.
No, it looks like a meshing for computational fluid dynamics.
Okay, not that sophisticated. The thing that you see around it is something that's called an octree. So if you've ever played a video game, a third-person shooter or something like that, one of the things that you'll notice is that the assets on your disk will run into the GBs. You have 10 or maybe more GB of stuff lying on your disk. But when you play a game, it doesn't actually load all of that into memory. So what it tries to do is that the game engine tries to optimize what needs to be held in memory and what needs to be displayed based on information about how the space around you is partitioned. So for instance, if I'm in this room, I don't need to know anything about what's in the next room. And if I'm a game engine, I just need enough information to render this room. I don't really care about what's out there. So how do I actually encode or store that information? You'd usually do that in something that's called binary or binary space partition, or in this case, it's something called an octree. So what it tries to do is that it recursively tries to break up the graphical information that you have into smaller pieces in such a way that as I go out of this room, I know that I now need to look at a new set of data altogether. So that's, in a nutshell, what game engines try to do and optimize. So this is also very, very useful if you're dealing with things like maps and so on. Okay, but the interesting thing is most complex domains, and if you're developing any kind of application that involves a domain that's interesting, you usually talk about an object graph. And one of the things that you may have noticed is that, especially in the code examples, there's not too much of what you would call an OR mismatch between what you're modeling and what the graph actually looks like. It's not, in fact, it's almost 1:1. So I could draw something on a whiteboard here which represents, say, a banking kind of application, and you could pretty much transfer that almost directly to a graph. And that's one of the nice things about graphs. It's what we call whiteboard friendly. So it's possible to model something and pretty much transfer it as is to your graph. So in databases or RDBMSs, you normally have to find workarounds for things like circular references, and as far as querying is concerned, when you start having joins to yourself, self joins and so on, it starts affecting performance and how you actually reason about the system quite a bit. With graphs, that actually becomes a lot more straightforward. Okay. So we already seen a few examples with Neo4j. Now the next thing that I'd like to talk about is that modeling graphs is really, really important. If you've ever worked with binary search, we all know that if you have a poorly balanced tree, which is what you see at the bottom, it's a lot harder for us to do an efficient search, right? So you'd like your tree to be well balanced. The main reason why we want to do this is because we want to minimize the number of hops before we find 8, for instance, right? So that means you have to go from 4 to 6, 6 to 7, and then on to 8. In the other case, you have to go through a whole variety of hops to get there. So this is true even for graphs, right? So you could say that trees are a subclass of graphs. Graphs are a lot more general. But the same kind of principles that we're talking about in terms of structuring our data are still valid. So this means that if it is possible for us to structure our data in the graph so that we can find what we are looking for with a minimal number of hops, that makes sense, right? So for instance, one of the applications that we were building last year was a financial expense tracking kind of system. And one of the things that we had to do was build reporting around it. So what we tried to do was to try and aggregate information about what was going on a monthly basis. So we actually stored that information, the time information about saying things like these are expenses for May or these are expenses for March and so on in the system. So we tried to represent the notion of time and the reporting that we are doing against that in the graph itself. Yeah? And the reason for that was just so that it became easier for us to query. It became easier for us to figure out things like what's the total expenses that the marketing department in Singapore went through over the course of this year. So partitioning your data and organizing it in a way that is easy to query is crucial. It's not easy to get right. I think it's fair to say that the graph community is still evolving and people are still figuring out what are the best ways of doing this, but it's something that you'll probably hear more about in the future. So in particular, taking a look at Neo4j's language bindings, we currently have bindings for these major languages. There are more on the way or being developed as well. So there's Java, there's C#, Ruby. I'm sure there's a Python binding as well. There's even a Node.js binding which came out quite recently. Now the main difference between all of these is that there are two modes in which these bindings work. One is embedded, which means that you have direct access to the database and everything is a lot faster, but the database is essentially running the same process as the application. The other one is the REST server, in which the database is running separately, has a REST API, and you essentially call the REST API to fetch your data. The driver does that for you automatically, or the binding does that for you automatically. So the main difference, of course, is a trade-off between performance versus partitioning and convenience. So Neo4j.rb, the example that we just saw, runs on JRuby, and it builds on active model, as you may have noticed already. Won't really get into the Ruby specific stuff. Somebody asked a question about how you do migrations. So a common misconception when we're talking about NoSQL databases is that because a lot of them invariably don't have a schema, you don't need to do migrations. In my experience at least, that's not true, because what you do have is an implicit schema, right? So even if you're storing order information in Mongo, there are some fields that you're looking for. You may choose to have a name field or a date of order field or something like that, which you're looking for in every single order document that you have in your database. And that's true for graph databases as well. As your application evolves and changes, and you decide to store your data in various ways, you need to find a way of migrating it. Just to give you a simple example, you remember the location class that we had, and it had a single thing called name. Let's say that we wanted to break up that thing into multiple attributes. So let's say that initially we specify the name and the pin code together, and later we'd want to store the name and the pin code as two separate things. Then we'd want to run a migration to do that for us. So we'd want to go over every single location node that we had in our database, split the name field into two, and essentially then commit that to the database. So that's the kind of thing that a migration would do for you. It allows you to evolve your schema as you go on. The final thing is multitenancy support and versioning. So multitenancy essentially means that you can run the kind of queries that we saw on the console, and be sure that whatever queries you're running are going to run only in the context of a particular tenant. What this means is that if you have one instance of the application and it's built to support things like multiple customers or multiple companies, the queries that you run will be scoped to that particular company. So if I say give me all orders, the orders that I get will be relevant to my company and maybe not to what Andy has in his version of the system. Right? It's also possible to do versioning as well. Okay, I'm going to skip through some of this. That's basically how you create a new node if you're using the level 1 API. You open up a transaction. Every single thing that you do through the database to make a modification to the database needs to be in a transaction. Right? This is what you just saw, which is essentially that I can define a model. It extends from Rails model. It needs to have explicit properties in case you want to index them, but you don't need to do this. You can also define properties on the fly. Right? And that's what the full text index thing does. That little include right on top adds versioning support to the model. Okay. Let me just show you what's possible with versioning. And this is the actual, these are snapshots of what the underlying graph will actually look like. So let's say I start with a driver with a particular name. If you wanted to do versioning in a graph databases, this is one way in which you could actually do it. So I start off by creating a driver. We have version 1 in which we have captured the information about the name of the driver. The next thing that we do is that in version 2 we have said that the driver now drives a portion, right? And when we capture this information in the database, by the way, what we are looking at here is the internals of how versioning support works with Neo4j.rb. This is something that I actually helped build. If you feel that it's becoming a bit too much, that's fine, because this is more like the internals of how all of this works, but it may give you an insight about how you can model, say, stuff on your project. Yep. So we are saying that the driver is now associated in version 2 with a sports car, and the versioning support actually captures the details of the driver again, and also captures a relationship to the thing that we are now linked to. As we add more, you can see that the graph starts getting more and more dense. What this really allows us to do is that we can say things like, let me go back to version 2 of my driver, and it would actually create and break links between all the cars that you see right there. That's broadly what the versioning support allows us to do. So what we're essentially doing is, as we create multiple versions, we're capturing those versions as nodes in the graph and capturing relationships as well. And it allows us to go back and forth in time to figure out what is related to what. Okay. Something that's a little bit simpler is how multitenancy works. So if you have a tenant and you have, say, 2 orders, one for Dr. Seuss and another one for Winnie the Pooh, we can see that if you look for all orders for a particular tenant, this is what you'd get back. For another tenant, you'd get something that's completely different. The multi-tenancy support essentially ensures that if you create orders in the context of tenant 1 and another set of orders in the context of tenant 2, those 2 orders are unrelated and unlinked. So if you ask for all orders in the context of a particular tenant, that's exactly what you get back. The Lucene querying stuff is also scoped. So if you search for star who, you get back results only if you're in the context of this tenant and not in this one. Yep. So probably going to skip through some of the other examples that we have here. This is an example of what Cypher can do. You basically have to specify a start node, say a little bit of ASCII art right there. The arrow that you see represents the direction of the relationship. So it says, I like to get to from my starting point, which is node A, all the way to C, where where C knows B. So for instance, if Andy and me are friends, then I know Andy, I'd like to know who Andy knows. Right? That's what this particular query tries to do. And if you did that, that's the kind of results that you'd get back. You already saw the shortest path example, but this is how it looks a little bit clearer. So starting at either node 1 or node 2, which I'm storing as variables D and E, I like to find the shortest path from between D and E. The star to 15 basically means that we should have a maximum of 15 hops. Yeah. And what we get back is not a node, it's actually a path, which is a collection of nodes and relationships. So when you run this query, you could get back something like this. Yeah, so that represents a path, and the greater than signs represent direction. So in conclusion, yeah, and we are pretty much close to the end now. So graphs are a compelling way to store interconnected data. As you can see, we can actually derive insights based on the data that we have, and we can add more and more information to whatever data that we have available. The second thing is that when you're modeling with graphs, you typically don't have an OR mismatch, which means that it's a lot easier to model and to reason about how things work in your system. The final thing is essentially that graphs are probably a little bit more widely applicable than you think. And I think my personal belief is that some of the graph vendors are probably doing themselves a disservice by saying that it's complicated or it's esoteric or it's hard to use, when it's actually not true at all. So I'd encourage all of you to try it out. If you're interested in Neo4j.rb in particular, that's where you can actually find the code base. And that's pretty much it. So thank you. Thank you for putting up with this. And that's my contact information. Yeah. Any questions?
Yes. Are you using JRuby because Gremlin is built on Ruby? I mean, which is built on Java, or is there? Why are you using JRuby?
Okay. So the main reason why Neo4j.rb uses JRuby is because essentially that's how it works in embedded mode. So the graph database is actually available in the same process as the application. And if you want to do that, you can only do that via Java. Right? Otherwise, you'd have to have a language bridge that talks to the database. So that's the main reason. So JRuby allows us to have both Ruby code as well as Java code running together, and that's the main reason why. The Gremlin thing, Neo4j.rb actually doesn't have explicit support for Gremlin. It has support for Cypher, but you can execute Gremlin queries if you'd like to. And yes, again, the fact that it's running in JRuby helps because it's pretty much part of the same runtime. Yeah. Any other questions? Yes.
How is data stored in the DB? Does it have its own persistence, or does it use Lucene, or can it use other data sources?
Okay, great question. So his question was, how is the data actually stored? So for Neo4j, at least, the file format that it uses is published. Essentially, from what I understand, the way it does it is that it uses multiple files, so it exploits the fact that each node is stored in exactly the same space, right? So if you have 1,000 nodes, it has a fixed record length for each node that it stores. So you can easily figure out things like, if I need the 10 millionth node in the database, then I know exactly where to go in the underlying store to get it. So two parts to the answer. So as far as indices are concerned, indices are separate from the graph, but they're stored in pretty much neighboring kind of location. The actual graph store itself is essentially, the graph itself is stored using a record kind of format, where each record, or there's a 1:1 correspondence between a node and its record, and each record has a fixed length. That's broadly what it does. The same kind of thing is done for things like relationships and properties. So it tries to do things like optimize disk space by ensuring that if you define a property name in one place, the same definition is reused in the entire system. But that's still more of an underlying detail. Now Titan, which is one of the graph databases that I talked about earlier, has pluggable stores. So you can use Cassandra and HBase and choose what you'd like to use as underlying mechanism. Yeah. So yeah, to answer your question, Neo4j has its own format. Titan allows you to plug the underlying database using whatever you'd like to use.
Performance-wise, how big is it? Let's say if you want to search for the shortest distance between two points in Singapore.
Okay. So performance-wise, graph database is actually really quick. For those kind of queries, if you compare the shortest path kind of thing that you're talking about, if you did that in a relational database or pretty much any other technology, I'm pretty sure graph databases would outperform for that particular kind of query. You can try it out yourself. Now if you're talking about something that involves, say, 4 or 5 hops, it's not uncommon for queries to run in the milliseconds. And especially once the database caches in neighboring nodes and all of that, it tends to perform fairly well. So performance is an important strength of graph databases. I didn't have the time to cover that in too much detail, but that's something that's really important as well.
Most of the time, the current applications have its own database. voice data. So do you usually kind of do a matching, replicate the data to the graph DB, or is it possible to migrate all the data into graph DB?
Okay. So in my experience, at least the product where we use Neo4j, we use that as the only store. So we didn't have a need for using multiple databases or multiple database types. So in our case, at least, because we didn't have things like assets and we were not really doing, say, document management as part of the expense tracking system, we actually stored all of our information in one data store. But yes, it is possible to do things like migrate the data into the graph if it makes sense, and also to kind of partition that if it makes sense. So for instance, one of the things that you should not use a graph database for is to store binary data. So you can do that, but it becomes a waste of resources and it's not really what it's optimized for. So the thing that graph databases are really good at is reading data and running the kind of queries that we talked about earlier. That's the kind of thing that they're really good at. So if you're looking at binary storage, probably not. Yes?
Is graph database scalable and effective? Can you distribute it easily?
Okay. One of the things that graph databases are not good at is doing that kind of horizontal scaling. That's a problem that the graph community is actively looking at. One of the things that you can do, though, is that when you use things like multitenancy, you can think about doing things like so with multitenancy, what ends up happening is that you partition the graph into subgraphs, and the information that you have for one tenant does not really have anything to do with the information for the other. So you can think about entirely migrating data out of one database which contains information for one tenant onto another database altogether. So yes, you can do that, but the main thing is doing that needs you to have a knowledge of the domain of the application. Right, correct, exactly. So it's like a functional partitioning of the underlying database, but it depends on the application and how you structure it. So in the graph community, at least at this point, that's still considered to be an unsolved problem in terms of doing it automatically. Any more questions? Okay, so I think that's about it. So if you have any more questions, please feel free to catch up with me later. Thank you, and that's pretty much it.